Hello everyone. Hi, my name is Waqar Ahmed and I have a PhD in geology. So today I'm in front of you to discuss one of the most, fascinating aspects of Mother Earth. Since time memorial, our human civilization has been, dependent 100%ly on resources from Earth, which we get in the form of metals, various non-metals, and today I'm in front of you to discuss one of the most fascinating aspect of Earth which we get and which now fuels our modern economy, and it's oil and gas. So before proceeding further, I'd like to give a thanks to Dr. Johnathan Craig, and who is Vice President for ENI. ENI is an oil company, and through their initiative for exploration and production and an outreach activity, and for giving me this presentation, and Professor G.M. Bhatt, with I worked for my PhD degree, and Dr. Bindra Tussu from University College London, who is my mentor as well. So there are a couple of people who needs thanks of appreciation. So to proceed further, so my presentation will be based upon the oil and gas aspects of our Earth, and how do we dig up oil and where to look for the oil and gas, and why do we extract oil and why do we drill our Earth. So these all things and parameters we'll be discussing today in this talk. So proceeding further, what actually is oil? So it's a natural substance, we know for sure, and it's found in sedimentary rocks, and it has been generated over a long period of time by the process known as decomposition from little organisms, and it's a renewable resource on a geological time scale, but it's a non-renewable because it takes a huge more than a human lifetime, a human lifespan. It takes perhaps much more than that to form oil and gas. So we are using it up faster than it's being created. That's why we term it as a non-renewable resource. And it has been known since ancient times, and perhaps its use was not for fueling. It was used as lubricant, it was used for waterproofing, it was used for lighting, but for the fuel, we have been using it for just last 1 century, 1900s. And you can find it as a liquid, as a gas, and as a solid bitumen, and the first oil well was drilled by Colonel Drake in 1859. So when I was younger, so I have seen around, perhaps most of the young kids, they don't know about, we had, oil in practically every aspects of our life. If we want to cook, we'd use kerosene oil in our stoves. So kerosene oil stoves, we cannot see them. And even for lighting purposes, we used to have gas, powered by kerosene, a small thing with which we today use. It's a rare thing to see now. So, and in our language, we used to say mitti ka tel. So mitti ka tel, I used to think like it's similar to extracting, like we crush mustard. सरसों को कूट के जैसे तेल निकलता, मुझे ऐसे लगता था मिट्टी का तेल भी कुछ ऐसे ही निकलता है. So then when I took geology, and then I came across, and then I understand, it's a bigger concept. It's a far more complex than simply thinking. Perhaps I was right. It's a byproduct of our Earth. But what I used to think, like mustard, and it's not simple like that. So in the preceding section of my presentation, we'll come to know how actually we get it out. So for the next, we need to know, since it's mitti ka tel, like mitti means soil, so we have to know what's inside the Earth. So this is a wormhole picture of our Earth. So you can see there are main 3 layers. The outermost, it's crust. It's more like a skin of an apple or an orange, so very thin. And then when we go down in this brown chocolate color, you have mantle. And then inner 2, yellow, and the grayish whitish one, these are the 2 parts of the innermost, which we call it as the core. The outer one is outer core, and the inner core is solid. So basically 3 layers: crust, mantle, and core. Core is further consists of 2 parts. So this is the basic what's inside the Earth. And now how do we get, where does the oil stands in between this? So if we'll see a cross section, we can see the crust. It's the topmost in green color. and nobody has ever drilled deep to the mantle. So whatever oil we are getting, it's just in the upper crust, upper part of the crust, you could see. And then we have mantle, and then we have discontinuity. We call it as Gutenberg, named after the founder of this discontinuity. And then we have external core, then we have Lehman discontinuity, and then we have inner core. So these are some physiographic characteristics of our planet Earth. So the highest Mountain Everest is 8,800 and something meters, and now this height has changed since of the last earthquake in Nepal. And then we have the deepest point, that's the Mariana Trench, that's almost 10,863 meters. And then Gutenberg discontinuity, it lies around 2,900 kilometers, and then Lehman is 5,200 kilometers, and the total Earth's radius is 6,370 kilometers. So, like I said, I mean, we can compare the internal structure of Earth with an apple. I mean, like the peel outside, it resembles the crust, and then the pulp, it resembles the mantle, and the stone, which lies exactly at the center of an apple, it's similar to a core. So, proceeding further. So, like, I mean, oil and gas, like I said, it is made up of from organisms. So, we need actually life for that. So, to search for the oil and gas in particular rocks, what does geologists do? They try to know all the complete history of evolution of our Earth. And compare it on and fit it on a geological time scale. So if you see, this is a simplified time scale, I mean, mostly cartoonized. So this is 4.6 billion years. It's since the formation of our planet and particularly solar system. So roundabout at 4.4 billion years, we get our oldest rocks on Earth, which has been dated. Like, we don't know prior to that if there is any record. So from the oldest rocks, we know that Earth is somewhere around 4.6. And then, right, I'd like to bring your notice onto the 543 million years. Right from 4 up to 543, we had absolutely, we can say, no signs of life. Yeah, there are some oldest fossil cells. There are some Adjacara fauna, which lies in Precambrian era, which call it as Precambrian. Right at this 543, we call this as Cambrian. After this, an explosion in life started. There were multiple factors for that. The environment was more conducive. We had oceans, fresh water. We had fully grown atmosphere, which could save us from the harmful radiations from sun. So it was a perfect scenario, and all the building blocks, the molecules, they were present at that particular time. So that point, at around 543 million years from now, they give rise to different species, I mean, of organisms, complex organisms. Before that, there were like eukaryotes, prokaryotes, just the single unicellular organisms. So after the Cambrian, we get complex forms of life. So the picture which you are seeing here, it's a typical trilobite, which is a characteristic of Cambrian, which marks, and then this is the Cambrian period, 543 up to 510. And then we have Ordovician period. This is all in the Paleozoic era. Before that, we have no action, we call it as a Precambrian era, which is before 543, which we go like to up to 4.6. We informally call it as a Precambrian. These are further, there are further some subdivisions, but I won't go into the details of that because that will be way out of our present focus. So in Ordovician, we had typical radiation of animals in seas. I mean, we get mostly predators in the form of mollusks, various bivalves, small microorganisms. And then in Silurian and Devonian, we had the appearance of fishes. I mean, the life is still in the water at this point of time. Mississippian and Pennsylvanian periods, they are a part of Carboniferous period. So in this period, the life, it started to move onto the land. And simultaneously, there were plants. They were started to grow. And they provided sunshade, they provided food for the animals, they provided a chance actually for animals to move from water up to the land. So majority of our coal seams, all in Carboniferous period, all over Earth, they belong to this period, these two periods. And then after that we had Permian and Triassic, that we get advanced amphibians on land now because we have all the foliage, we have shade. And then those amphibians, they gave rise to reptiles. And in Permian, after Triassic and Jurassic, which Jurassic is famous for, dinosaurs, everybody knows it. So in Triassic, Jurassic, we had dinosaurs were like huge organisms. So we had ample food on Earth now by the time now, so that dinosaurs, they could survive on it. And then similarly, if we go out in Cretaceous, in Mesozoic, we had plants as well. We had mammals, rise of era. And then in Cenozoic era, it's typically called as age of mammals. And now among all the mammals, reptiles, now mammals have started to radiate. And then we get horses along 5 million years, and then elephants along 1.8 million years. And in the last, about 0.001 million years ago, we had the appearance of humans. So this is, in the nutshell, a geological time and evolution of life altogether from, right from the conception of Earth at 4.6 billion years. So moving on to the next. So in geological time, if you'll see the globe, present globe, our Earth continents, they were not there before. I mean, they have been brought onto the present position. This is a concept called as plate tectonics. I'll just give you an elementary idea of plate tectonics, since we are not discussing plate tectonics today. But this plate tectonics were very much active in making modern total global oil reserves of our world. So if you could see, this is a map of our Earth in late Proterozoic, which age corresponds to about 650 million annum from now. So on the left side, you can see the legend. There is ancient landmass, modern landmass. These in transparent boundaries. This is modern landmass. But ancient landmass, it's somewhere confined here into the South Poles. And then we have different setting subduction zones and seafloor spreading ridges. But the point is, what I am trying to convey is the plate tectonics. You can see India somewhere in the middle and near to the equator, right? But this is not where India is at the moment. India lies somewhere here, right? So you could see an Antarctica down at the dome and Australia somewhere here. So this all assembly of continents, it's been broken. It's not in the present form as if it was then. So something happened and plates starting to move, which is another concept, but sticking to this current focus, I'll move forward. So why are we actually discussing this moving plates? Because in different continents, we get different oil reserves at this point of time. Recently, Iran had another discovery. So why are these countries getting oil from specific places? So to know that, we need to understand the position of continents. They were since the conception of hydrocarbons. Since, like I said, hydrocarbons, to make oil and gas, it takes millions and millions of years. So to make that, this present position, which the continents are now, they were not there. They were clubbed around the equator so that the conditions were perfect. There was ample amount of sunlight, and where there was a really large number of organisms which could form into like the source of the hydrocarbons. So you could see the India, how much flight India has taken, right from down South Pole, right up to the Eurasian plate, right? The top and docking it, and formed a huge mountain chains, perhaps the largest mountain chains of our Earth, the Himalayas. So this is a concept we should discuss somewhere else, but I just want you to know that the continents which we get oil on, they were somewhere else in the time the oil started to make. So moving on to the next. This is again a time scale, just a simplified version. So on the top, you can see we have super eon, which we call it as Precambrian, and Precambrian is the largest one. And surprisingly, we have absolutely almost no complex life in this Precambrian eon. So it is further divided on Hadean. Hadean is a Greek god Hades, derived from that. And in Hadean, we had absolutely not even land. All the earth, it was all, molten and a sea of lava flowing everywhere. And then we have Archean. After that, in Archean, we started to have a solidification of lava, and there were some continents. The first land started to appear on Mother Earth. So that's why we get some few evidences of some bacteria, and that too we call them extremophiles. Since the conditions were not conducive enough for organisms to sustain, so that's why they had some primitive extremophiles type of bacteria, first life, if we get in Archean. And Archean further divided into Paleo, Meso, and Neo. And then we have Proterozoic, and Proterozoic is further divided in Paleo, Meso, and Neoproterozoic. At this Precambrian time, Earth's crust, it was trying to adjust itself. It's still doing now, but minus life. It was just the Earth's crust and Earth itself and its atmosphere. So all this time period, it encompassed the conditions it tried to make the conditions for Phanerozoic eon to come, and in Phanerozoic eon, what came? Life with it. This started here, Paleozoic, and Paleozoic starts with Cambrian, which we discussed in my previous slide, and Mesozoic and Cenozoic. So what I am trying to say is, out of all this time span, starting from 4.6 up to 0, life started just around about 500 million years. So this much long time, it's all no life zone. Excuse me. Next. This is somehow very fascinating. If we talk about this history of Earth, 4.6 billion years, and if we try to compare it in just 24 hours. So, like, started at 12 in the morning, origin of Earth happened, right? And then first rocks, they appeared just at 2 o'clock, like in just a matter of 2 hours. And then first organisms, we had at like 2:30, 2:30 baje karib. And then we had first common shellfish. First fish is at 11:40 or something. And then we had first land plants. They were like at 11. And then land vertebrates, dinosaurs, first grass. And first humans, they have appeared just 2 minutes ago. If we'll compare this to a 24 clock, from 12 in the morning to the 12 the same day. So humans are here just for like 2 minutes on this planet Earth, and see what we are doing. Next. So actually, let's come back to oil. So this was about Mother Earth. What actually oil is? On the bottle, if you see on the left side, this is a crude oil. This is raw form of oil. This is the oil which we can, use it for, we extract kerosene from it, petrol from it, diesel from it, even natural gas sometimes. For fractional distillation, this is a process in chemistry which we do it afterwards. So that's again another concept. So actually, what is oil? Oil and gas, they are a mixture of different hydrocarbons, like the name suggests, hydro and carbon. So we have a backbone of carbon, which you can see in the figure, these black dots. This is a backbone of carbon, backbone. And then these carbon, they are surrounded by molecules of hydrogen. So we have a backbone of carbon and then fitted by different molecules of hydrogen, and they form a long chain altogether. So next, and like I said, they are predominantly, it's the more chemistry, like the structure. A carbon has a nucleus, and then it has 6 electrons in its shell. If you could see, 2 in innermost and 4 in outermost. So in the outermost shell, the 4 electrons, they make a possibility of 4 hydrogen atoms to come and get fixed at 4 different corners. So similarly, we have we have electron at the center. So we can get, if there is just 1 carbon and 4 fitted at the 4 different places, then we get CH4 formula, which we call as methane. And similarly, if there are 2 carbons, and then they can get 3 each, so C2H6, we get ethane. Similarly, we get propane. If there are multiple 3 carbons, if there are 4 carbons, we will get butane. If there are 5, and similarly the number goes. So if a long chain of hydrocarbons. So one thing I need to tell you, that methane, ethane, propane, and butane, they are the simplest form of hydrocarbons, and they are the only 4 which exist in the form of gas. The liquefied petroleum gas, which we use in our household daily for cooking, it's made up of butane. And it is odorless gas, and they use a specific kind of gas to detect leaks if there are any, since it's a highly flammable gas as well. So as the more carbon atoms add up, the higher hydrocarbon density. So that means you won't get them in the form of gas, you will get them in the form of liquid. So you can see C1 to C4, it's gas, and then 15 up to C15 we have liquid, and above, if there are more chains, more carbons attached to each other, C16, and then we have in the form of solid. Moving on to next. So what actually is the origin of this oil again? In the bottle which you saw, the black crude oil, what actually makes up that? So these are plant planktons, and on the right there are animal planktons. By planktons, which means they are really, really small organisms, not even visible through a naked eye. So these organisms are that much small that like 10,000 of them will fit on a tip of a needle. You can really imagine how small these are. And these organisms, they live in n number in the ocean. There are millions of them organisms. And 10,000 of these bugs would fit on a pinhead. They are actually those small. And most oil and gas starts life as microscopic plants and animals that live in ocean. So whatever oil or gas you are using now, they were once life, they were once living. They were part of a living organism, yeah, of a plankton, which maybe we cannot see. But they were part of a living organism that lived in the ocean once upon a time. So moving on to the next slide. So this is a typical origin of oil and gas, the things, planktons, which I term. This is what you see them in real life. I mean, in oceans, you can say this is a typical red algae, which we call as a dinoflagellate. So it's a principal, component of oil and gas. And we can see plankton, I mean, where there is a rise in ocean currents. I mean, the warm water, upwelling water is rich in nutrients. So it brings with itself nutritious small microorganisms in search of food. So we get, a company, like more than a company. I mean, it's like a hujum, जिसको हम अपनी उसमें कहते हैं, like a bloom, dinoflagellate bloom, and they give water a red water tinge. They are red-colored algae. So this is what plankton looks like in real life. Moving on to the next slide. So these planktons, they are in oceans. Okay, so they die. Someone die. Yeah, everybody dies. So they come onto the seabed. So two things may happen. If there are animals on the seabed, they'll feed on these particles, and sometimes these animals they can also die, and they'll lay on the same seabed. So it's a circle which goes on. So in the seabed, in short, seabed receives a lot of organic mush in the form of raining mush all the time, and this mush is then made into oil and gas, converted into oil and gas. Moving on to the next. So if there is little or no oxygen in the water, so animals cannot survive, and the organic mush, it starts to accumulate because there are no bacteria to eat it. Okay, and along with this organic mush, there are sediments as well, parts of different rocks which have been coming out through rivers and all. So 5% organic matter. If there is in any rock, we'll call it as a black shale. Just 5%. We don't need much. So on the right, you can see this is a typical thin section of a black shale. You can see laminations in it. So through the compaction and overburden, all the sediments, they are transformed into a rock, which we call it as a shale. If the rock has buried with itself some organic matter, there is a number. If there is more than 5% of organic matter in that, we'll call it as a black shale. Okay, and this black shale, it happens to be the source of most of the oil fields at the moment. So we know that oil is found in sedimentary rock. So let's know about how the sedimentary rock actually is formed. This is formed by deposition and cementation fragments derived from breaking apart of ancient rocks which already are there. So weathering occurs, rain, ocean, wind, and snow, frost, rain, wind, heat of the sun, it detach rock fragments and make debris out of it. These fragments are carried towards the valleys by streams and rivers. On their way, rock fragments knock together and break. They are carried along and laid down as sands and pebbles. On the left, you can see an image. In time, weight of new debris squeezes and hardens older debris, which becomes sedimentary rock. Like I said, with weight and overburden, like you put on stacks of different books, right? So the book at the bottom will have an ample amount of pressure from the top books. So it's similar to that. Next. So oil and gas, we call them as fossil fuels, right? So also fossil. So this is a slide which tells about how fossils are formed. In picture A, you get an organism has died. Okay. In picture B, a lot of sediment sediment comes and it has buried the organism whole together, preserving all its body parts and its original form. Okay. In C, it's been again, stacked upon, buried upon a lot of pressure, and somehow since it's in a terrestrial environment, and then there is erosion. Suddenly there is a landslide. So the top cover goes, and we get a fossil inside, which has been perfectly preserved in the rocks since time immemorable. Next. Okay. Now we know that on seafloor we get different types of planktons and all stuff. So how those planktons, they actually turn up into an oil? How do they make an oil? So this organic matter, oil is generated from this organic matter derived from the decomposition of plants and animals deposited in the sedimentary rock. During millions of years, the organic matter is transformed into oil by action of bacteria, temperature, and pressure. So this is a magnified image of this place. So This is a scenario of an earth. Here there are pre-existing rocks, so water, river, rain, they are eroding these rocks, bringing out sediments. There are some plants as well, some organisms as well. So it's eventually ending up in sea and at the bottom of sea floor. So you can see there is an company of full of different types of organisms on the with the rock. So this thing. So like I said, at the bottom of the soil, in geology we call that rock which has all the organic matter in it a source rock. Okay, we have nutrient supply from the top, and then in ocean there is a scenario in oxygen levels. I mean, the water level near to the air, it will be enriched in oxygen. You can see the oxygen. As we go deep, the oxygen trend follows a decreasing trend, and then a place near about at the bottom, we have total anoxia, right? Not even no organisms can sustain in this anoxicum. You can see a fish, a dead fish here, but a live fish here. So whatever nutrient supply is falling in this part of the zone, it will be preserved. It won't be decomposed. That's for sure. So this kind of setting, we need actually this kind of setting for our oil and gas to form. Moving further. So this is a typical, again, sketch of hydrocarbon source rock deposition. Where do we get these source rocks? Not in every environment. We don't get in every part of the earth source rock. So these are flooded forests. These plants are buried and decay in stagnant modes. This is a lake type of environment. And if there are some planktons, they will also go, and this is a stagnant seabed, and they'll deposit here. You can see these black. These are actually how coal forms. And this is oil and gas right here down. This is a typical scenario which, I mean, there should be like flooded forest, the environment should be lake type, kind of with the stagnant seabed, because there are open seas, there is a lot of waves going on, so they won't let the organic matter to settle down. They'll just keep them in transport. So this kind of settings is very necessary for source rock deposition. Moving on to the next slide. So in ancient earth, so since I said the oil and gas, it takes millions of years. This is a plate tectonics, again, image from ancient earth. You can see on the left, this is South America. On the right, this is Africa. In the north, this is North America. And in the south, Antarctica. And this is India, somewhere here. So the red dots, they are all major oil fields global. So you can see during mid-Mesozoic times, around 150 million years ago, conditions were just right to build up huge thicknesses of black shale source rock. Okay, the world's main oil deposits all formed in warm, shallow seas where plankton bloomed, but bottom waters were deoxygenated. Deoxygenated by mean anoxia. If there is oxygen, then there are bacteria, they'll decompose it, they'll eat away every organic matter, so the organic matter won't be preserved. We need minus oxygen-less environment. So this is a picture of 150 million years ago. So you see the conditions wherever we get oil today, they were exactly right. They were not at that time at the same place which they are today. Moving on to the next slide. This is a typical picture of source rock. It's a place in Italy, and it's a Jurassic age. So you can see rhythmic Jurassic, limestone, and black shale sequence in Italy. So these shales are all black. These happen to be a source rock. I mean, these shales have for sure organic matter in them, because they are black, and it has to be more than 5%. Okay, the next, this is again a picture of black shale, which happens to be a source rock, in Kimmeridge clay, which happens to be in UK, in North Sea, so which has up to 50% of organic matter. This clay has a lot of organic matter, and it's a main source rock for North Sea oil fields. There are famous oil fields in North Sea. So the oil fields, they have the source rock right from here. So this is an outcrop picture. I want to show how does a black shale in actually real world looks like. Moving on to the next slide. Okay, this is something we want to know of an source rock, if it's potentially a good source rock or just a feeble amount of organic matter. So this is just a plotting this. You will learn that if you do research in petroleum geology. On the left you have depth, and then these are some parameters, TOC, hydrogen index. So this is a particularly of a case study of Congo Basin in Congo. So I'll move on to the next. And okay, oil and gas, how does it origin? Okay, we have source rock, we have everything. Now what? We need, by source rock we mean there is organic matter, and now we need to cook that oil and matter if we want to turn up into then oil. Okay, and this is a simple figure. As black shale is buried, eventually it is heated. जो चीज़ दब जाती है उस पे फिर pressure and temperature, because of temperature and pressure, it will increase its temperature. And organic matter is first changed by the increasing in temperature into kerogen. We call it as a kerogen. It's no more an organic matter, and kerogen is a precursor form of hydrocarbon, solid form of hydrocarbon. So we get at around a depth of 1 kilometers and temperature at 30 degrees, we get to form formation of kerogen. And then as the depth is increasing and the temperature is increasing, at around in the range of 60 to 120 degrees, we'll get oil from the same kerogen. And at around 150 degrees, it is changed into gas. A rock that has produced oil and gas in this way is known as source rock. Okay, now you can understand why did I call this as a source rock. This is a typical temperature and depth. With depth we mean pressure. How many pressure is also there? Overburden pressure. So temperature and pressure, they are important parameters for a source rock, for cooking of a source rock, so that source rock is a potential, actually a source rock, we can produce oil and gas. Moving on to the next slide. We need to know now if this source rock is hot enough. So this is a maturity analysis. By studying different slides, the organic matter, we have come across 5 categories. If the temperature is less than 120 degree, then it's immature. 120 to 150, it's early mature. 150 to 80, it's late mature. That means it will produce oil and gas. 180 and 120, it will produce gas, and greater than 220, it's overcooked. We won't get any hydrocarbon in the form of oil, any form, oil or gas from that. So this is for the sake of research purposes only, just to give an overview what actually parameters we know, we calculate before proceeding further for exploitation or exploration. Okay, moving next. So we have a typical trend which we see in our real environments, in our typical basins. We have increasing source rock maturity with temperature and with depth. You can see the depth in kilometers on the left side. This is a picture of a typical basin of a North Sea, which I showed the picture about in UK. On the right, you have a depth in kilometers, and then adjacent to it, we have temperature in degrees Celsius and the color coding of source rock maturity. You can see the bottom at the black, it's beyond 6 kilometers and the temperature is exceeding 200. So it's all black. We won't get any form of hydrocarbon from it. It will immature. It's similar to you want to cook in a pressure cooker. If you are cooking your food in pressure cooker, if you will cook it for overtime, it will all turn into black. And it's not eatable. It's not potable then, right? So to make your food tastier, you have to cook it for the ample amount of time. Not less, not more. If you'll cook it late, then it's less cooked. You cannot eat it either. So if you cook it more, you cannot eat it as well. So you have to cook in ambient range. So similarly, it's the same scenario applies here. We have oil, different organic matter, and with pressure and temperature, oil fields here and here. Source rock lies somewhere in the bottom, and due to these lines, these are faults, and they form conduits. Oil and gas has migrated up into the rocks. Moving on to the next. Okay, now the source rock has formed out. Where is the oil? Where does actually this oil places itself? So hot oil and gas, they are less dense, and the source rock where they actually are originated. So what they do, they won't stay there. They try to migrate up through the rock in the same way they like an air bubbles underwater diver. If you've seen an underwater diver, there are constantly air bubbles coming out. You can literally see the air bubbles. Because why? Air is less dense than water. So that's why water cannot trap air inside it for the long period of time. So that's why this is a picture. We have rocks, magnified scale, different rock sediments. We have spaces in between them. So the rising oil and gas eventually gets trapped in pockets in the rock called as reservoirs. One, we have source rock. Next, we have reservoir rock. By the name reservoir, you can say it can store oil and gas in its pores. Okay, moving on to the next. And again, expulsion and migration. Okay, somewhere, we have not seen it, but somewhere people, have reportedly seen oil and gas coming out. If it's formed at such greater depth, why do we get oil and gas seeps on the surface? So it's actually, on the left, this image, if you'll see, this at the bottom, it's the source rock. I mean, where all the sediment has been converted into kerogen and then kerogen into oil and gas. So if I'll magnify this migration, you can see tiny, tiny oil droplets. They are moving towards up. They are moving across the permeable layer. They'll move up until they get trapped by an impermeable layer. By the chocolate color, this is impermeable layer 1 and 1. Okay. As far as this impermeable layer is there, oil and gas will be trapped in there. But in Earth, all the plate tectonics, like I said, they are moving. So that means there are external stresses occurring on rocks. So if there are stress on a rock, the rock will break. There will be a fracture. If this impermeable layer is fractured by external stresses, so the entrapment, the seal, it's broken. So it allows oil molecules to move up against the gravity because of the change in viscosity and density. So the direction of arrows here, they see the migration of oil and gas. And on the surface, we see oil and gas and tar seepage in the form of small ponds. I'll show those pictures. There are some pictures in the next. Okay. Moving on to the next. This is a pitch lake in Caribbean, Trinidad. So look, this is an oil seep. On the surface, what does it look like? So I showed you in the previous slide how the oil has come up. This is Kalimantan in Indonesia. You can see typical oil seep somewhere in the forest. And here it's a 1924 picture of Iran. You can see an oil pond, simple, a pool. Moving on to the next. To know, this is the North Sea, Central North Sea area. To know about, I mean, North Sea, it's oil field. So for knowing the oil field detail inside out, what does geologists do? They make cross sections different. So this is these are refineries. These are some, not refineries. These are, you know, for taking oil out, drill holes. So bore holes, they are drilled. So this is a structurally complex. I don't need to explain this to you. It's an east-west trend from here. So we had different these structures, salt domes. Okay, we have chalk. Salt is impermeable, so that's why it makes a good reservoir rock. So it can trap any oil which is coming from beneath. And then we have chalk, we have Jurassic rocks. They all form an impermeable layer. So that's why we get oil and gas localized around them. Moving on to the next. And this is again another section through Ekofisk oil field in Norwegian North Sea. So you can see there's this salt plug. It's growing and it has pushed the source rock a bit further. And this growing salt plug, it has fractured the overlying chalk, which is impermeable layer. If this salt plug had not grown, the oil would have been just localized here. Now the salt plug has grown, so breakage into chalk, and which has allowed oil to move inside here, and the gas escape, and we can see North Sea, the gas coming out from the bottom of the sea. So this is why it happens. The geologists, they try to go underneath the environment. Why does this is happening here? Moving on to the next. Now in totality, I mean, like you may have now analyzed, like petroleum system, it's a complex scenario altogether. We have pressure and temperature first acting on a source rock, and then we have reservoir rock, and then we have entrampment. Three things, major three things. So pressure and temperature occurring on a source rock, and then generating expulsion of hydrocarbons, and then there are a rock who carries them along, and finally ending up in a reservoir which has an entrapment method, which has a seal, and it can trap it oil there. If there is a fracture any in the reservoir rock, the oil will eventually come up in surface. So we're not lucky every time. We have to sometimes go drill deep down on the earth and get the oil out. Okay. Moving on to the next. This is how does a petroleum system reservoir rock looks. I'll just make that slide to go again. Okay. This is a highly magnified picture of a sandy rock water-filled pores. They are shown in blue. Now these pores are filled with oil. That's why these are black. The permeable strata in an oil trap is known as reservoir rock. Reservoir rock should be permeable because it should be have pores, similar pores. जगह होनी चाहिए उसके पास ताकि वो अपने अंदर तेल और गैस को समा पाए. फिर वैसे ही reservoir rocks have lots of interconnected holes called pores. They absorb the oil and gas like a sponge. Okay. Moving on to the next. the physical characteristics of oil. Since I talked about pores and porosities, now a rock should have a good porosity as well as permeability. What is porosity? Porosity is volume of the empty spaces inside a rock. We see a rock, we see just a full solid, but microscopically it consists of micropores. That is called as porosity. It is the ratio between empty spaces and the total volume of the rock. Okay, the porosity higher values can be about 30 to 32%, but it is possible to produce oil from rocks with a porosity of 3 to 4%. 3 to 4%, even less than that. Shales have in 0.1, 0.2 porosities, nanometer porosity, which we call it. So these are some characteristics which we should evaluate a rock about before, investing money to drill oil well. To drilling an oil well requires a lot of money. And second is permeability. What actually is permeability is a property that allows passage of some fluids through a rock, not essentially oil. It can be water. We have groundwater aquifers. They also require same physical characteristics of oil. We don't get groundwater everywhere. Why? Because we don't have a rock which can store water in it. So wherever the places we get these conditions, we can have water as well as oil in them. And some examples of porous rock that can be bearing are seen in these sections. This is limestone, this is also limestone. And limestone is made up of, it's a biogenic type of sedimentary rock. You can see nummulites fossils in it, and here it's all again limestone with numerous shells and fragments and all. So limestone is a good reservoir rock. Shale is a good source rock, limestone is a good reservoir rock. So these reservoir rocks, they have like cementation, compaction. You can see on the left, these are pores in blue colored. These are all pores, and these are sand grains. Gas can be stored in them. So if gas is stored in them, and then similarly water is also stored in them, oil is also stored in them in numerous pores. They can make spaces for oil, water, or gas, whatever is present. Okay, moving on to the next slide. This is a typical reservoir rock, which is a Karoo sandstone in Tanzania, Africa. Because sandstone, there are numerous sand grains, and sand grains, they have numerous pores in between them. So compared to shale, sandstone is a good reservoir rock. Shale is a good source rock. Limestone is a good reservoir rock. It can be source as well as reservoir as well. Okay. Moving on to the next, this is a typical picture of a sandstone in Jodhpur, Rajasthan, and this is again producing a reservoir rock, potential reservoir rock, sandstone, and there is this huge fort standing on this. Okay, moving on to the next. Now we studied about source, we studied about reservoir. Now let's talk about traps, which actually trap the rock. If there are no traps, like आपके पास बर्तन नहीं है तो खाना तो बनेगा ही नहीं. बर्तन भी ढका वाला होना चाहिए if you want to cook it. Right? Gas bhi chahiye. So there are particular like 2 to 3 things. There are ingredients for a good meal to prepare. Similarly, we need to know about 3 things for a petroleum system to produce oil. So, one, like I said, source, then reservoir, and finally the trap. Some rocks are permeable and allow oil and gas to freely pass through them. Okay. Other rocks are impermeable and block the upward passage of oil and gas. Okay. Where oil and gas rises up into a dome structure. In geology, we call it as an anticline. Capped by impermeable rocks, it can't escape. This is one type of an oil trap. You can see zigzag. This is in 3D. This is like a wave, right? Like an anticline like this. So say for example, we have a source rock here, and this in white, it's a impermeable layer, and this one is permeable layer. So all the oil, it has come up to here. Now it has an impermeable layer at front. It cannot move. The gates are closed. So it will stay there. So this type of trap, the oil has been trapped. We call it as a dome trap, where impermeable layer is above the permeable layer in the form of an anticline, which makes spaces for oil to stay there. We call this as a typical oil trap. Okay. Moving on to the next. Oil and gas is contained in the sedimentary rocks in traps. Let's talk about traps a bit. The sediment thickness, see on the left, sediment, how thin is it? And then gradually its thickness is increasing because the sea bottom sinks. Some rocks contain large amount of organic matter. They are named source rock. The source rock produce oil and gas, like I said. And then movements inside the earth crust can fold, break these sedimentary rocks, and accumulation zones can be generated. These zones are named as traps. Okay, the oil and gas produced by source rocks is able to move through the rocks and becomes trapped. This movement is called migration. See in this figure, this is a typical sketch. So you have traps here, and you can see arrow showing the movements. A trap needs the presence of an impermeable rock. This is very necessary. A seal rock with a convex shape and a porous permeable rock, which is a reservoir rock. And when the trap is big enough to contain a substantial or oil accumulation, it is called as field. Because like I said, to exploit any oil field, you need a lot of money. So you have to know how big the field is. Can we sustain ourselves by exploring that field, by exploiting that field? We don't want to end ourselves as bankrupt. We don't want to lose money. So this image is magnified here. We have a reservoir rock and then covered by a seal rock, an impermeable rock. Okay, a reservoir rock. I think you are getting my point. And then moving on to the next slide. And this is the type of oil and gas accumulations, like traps. The one which we in geology we call as stratigraphic traps may occur where the reservoir rock thins laterally or is pinched out into the surrounding seal rocks. Like this. You can see it's pinching out, it's closing here, it's not extending like all together here. So we can get a trap here, we can get oil here, and again here a trap pinching out stratigraphically has changed. Second is structural traps, which is typically are often found along the edges of salt domes, in the crests of anticlinal folds, or along fault lines. So this is a salt dome. On the edges we get structural traps, or this is a fault. Along the fault line we get structural traps. So we have three, stratigraphic and structural, and oil traps, the previous one which get. Distances from the surface are greatly reduced for clarity in this cross section of underground strata. You can see on typical, this is a fold. How does a fold look like in a nature? Again, this is a fold. There is a fault here. So this anticlinal fold explosion sea cliff through south of Cardigan, West Wales in UK. Moving on to the next slide, we have like now to study just an elementary idea of folds and faults. Okay, this is an anticline moving up, and this is like a V shape, we call it as syncline. And then we have, these are symmetrical folds, this is an asymmetrical fold, and we have recumbent fold where the fold axis is almost horizontal, and this is overthrust where one fold rides above the another fold, we call it as overthrust. And similarly we have faults, normal and reverse. This is a normal example, and this is a reverse. We have a fault plane where the movement is towards downwards, and then we have again the fault plane where footwall is below and the hanging wall is above. So this is reverse fault and normal fault. So in these type of normal settings we get oil and gas. Now let's talk about a detailed structural traps. This is an anticlinal fold, you can see, yeah. And if there is a permeable and semi-permeable layer, it can form an absolutely good, anticline in Ordovician black shale, Langrong, West Wales. And now, characteristics of a typical structural trap. If somehow you can understand, I mean, these are the images from various techniques, seismic cross sections. We can, want to know under the ground. We send seismic waves to know about the changes in lithology, any change in density or variation. So you can see, this is a contour map. So these are some characteristics which we want to know of a place. If we have established that there is a dome or a structural tab beneath. So to know further how correct we are, we do some analysis. So this is seismic cross section, contour map, and block diagram. Moving on to the next. This is geological cross section through Eakring oilfield Midlands, UK. So again, you can see at the top how does the ground looks like, but beneath we have a huge anticline, and which have been topped by an impermeable layer for the limestone. So it is forming a trap. So oil is sustaining it. We don't get seeps here. Okay. Moving on to the next. So the search for oil gas. This gentleman, he is Dr. Johnathan Craig. So I must know that. I must tell you to do. So these are pictures from 1985, and Dr. Johnathan Craig, he is senior vice president, like I said, in exploration and production in ENI. So there are different techniques, like if you want to study any area, like say for example, this is a small map, So it's a potential oil and gas. So geologists need to go gather all the information from there. Do not miss it because it involves a lot of money. And we call it as mapping. These are some aerial pictures taken from an aeroplane. And then we know how the trend, how the stresses are moving to know the better, things of. This is out of your focus, but at least you should be familiarized with these concepts. Moving on to the next. We can do geological mapping using from space. Now we have satellites. I mean, this is a typical satellite image of Srinagar city. You can see Anantnag here, Sopore here, satellite. So this, all the snow cover, it's been in purple color. So from this information, you can tell the extent. I mean, the satellite image, it's a remote sensing technique to know about the places. And moving on to the next, this is again a satellite image data of Kashmir. You can see the Jhelum river flowing, and all the settlements, they are in violet or purplish color. So this is a type of remote sensing technique which we can know about what's beneath the Earth's surface. Okay, moving on to the next. This is just a cartoon about going on a field trip. I mean, being a student of geology, you really cherish going to the field trip. This is like day one. I remember once when we went on a field trip and it didn't rain, and we all learned a lot and we all had a good time. So nobody knows when, because this is day first. They have never been to a field work. Moving on to the next. Okay, the search for oil and gas, geological field work measuring outcrop sections. One thing that geology does is it takes you places. This is a picture from the Salt Range, Pakistan, and it is the Cambrian succession at Fort Coosack, and December 2007 photo. So, moving on to the next. Again, some pictures of geological field mapping in Italy. Okay, moving on to the next. Yeah. This is Bagno di Romagna, March 1998. And moving on to the next. So sometimes some countries, they offer different transportation facilities. This is actually a personal presentation of Dr. Craig. So I wanted to show you pictures how geology, I mean, introduces yourself to the world. For being student, for opting career as a geologist. So this is something you will get to see in your lifetime. In Australia, a jeep. In Pakistan, a camel. Similarly, in India, a camel as well as an elephant. And in Libya, humans. Okay, moving on to the next. This is again pictures from field work. This is again in Pakistan, Sukur. And this is Tanzania. Sometimes you get to live in places which you have only dreamt about, in different camps. This is life as a geologist. On the top left, it's Tanzania, again Tanzania, Australia and Tanzania, in Africa and Australia. Moving on to the next. Yeah, this is what geologists do. And again, yeah, sometimes you get to travel in choppers as well. Okay, transport options 3, you can see. This is Papua New Guinea, transport options. And again here, you can see. And then yeah, geological field trip. Why do we have to go on these stupid field trips? So eventually you start hating these field trips as well. Who knows, but at least it's better than sitting in the desk all day like I'm doing. You mean we weren't supposed to bring our desks? So it's like in a more humorous way. So you end up sometimes in difficulties as well. Well, you go for field trips, you go out in the Mother Earth, you want to familiarize yourself with the Mother Earth. So you sometimes, have to face these situations. Moving on to sometimes the fieldwork takes you underground. This is an underground salt mine in Pakistan. See how does it look. This is all salt. And salt, it's an impermeable layer. It won't let oil to pass through it. So it forms a perfect trap. It's principally halite mines, okay? In Kevra salt mines. It's infra-Cambrian salt range formation. And then it's a really, high-tech in geological data integration. I mean, search for oil and gas just does not stop, end there, like knowing source rock, reservoir rock, and the traps, identifying this. No, you have to further, sequence stratigraphy, facies analysis, outcrop analogs, and data integration, WellCAD. I mean, you have to take in every aspect before proceeding further for, taking the decision to take the oil out. Okay. Eventually, if you'll take your field, as a research, you'll take research in geology, you'll end up knowing these things. This is again a geological map of Jammu and Kashmir. So different lithologies and different Mampidi, Pir Panjal range, MCT, Himalaya, Great Himalayas. Okay, moving next. And after the field works, you have to make a report. What did you do? This is my report on the field trip we took yesterday, and that's about it. And going on to the next. So all this lecture, why did you listen to me, or why did I was there? So with oil we produce energy. I mean, from these images you can see practically every form, if I am here sitting in front of you, I have come here from my home in a car which has been powered by a fuel from petrol. Okay, I'm using this computer in front of you, plastic, also byproduct of water. Oil to produce electricity. This electricity which you are able to see me, it's also because of electricity, oil. Cooking gas for oil heating. I mean, you can gas or oil heating. I mean, for winters, we have winters today. For oil heating, we use fuel. For road purposes, if you have a bad road, your car will be damaged, so you apply asphalt on it. It's also a byproduct of oil. Even in ship, huge oil tankers, huge ships, they ferry stuff here from one part of the globe to another. So it's again a fuel. Aeroplane. I mean, everybody likes air travel. If you want to be quickly somewhere, an airplane can take it. Car fuel. Everything, practically everything, it's supported by oil, if you realize. So how oil is in our day-to-day life, you can see how much. It's a typical scenario of our room. You can see the list is increasing. Right from curtains to plant fertilizer to candle wax to cosmetics, detergent, canned goods, synthetic rug, sneakers, plastic bottle, pen ink, compact discs, camera film, and paint. This is all byproduct of hydrocarbons. And this is oil in your everyday life. Knowingly or unknowingly, we are using it. Not for the fuel every time, but for other things as well. Moving on to the next. CDs, DVDs, I told you, plastic, fertilizers, food additives. The remaining 16% of crude oil is used for a range purposes shown above, as well as synthetic fibers, dyes, and detergents. Okay, on the left you see a picture of coal. I mean, yeah, burning coal produces a lot of smoke, so that eventually leads to global warming. And oil and gas, they emit 15 to 30% less CO2 than coal per watt of energy produced, and so hence renewable energy, it's clean, but not yet viable as fuel. We can't get windmills everywhere. We can't extract electricity from windmills at every part. So the role of a geologist from exploration to production. So this is what a geologist does eventually. Sedimentary basin evaluation and petroleum system definition, identify all the aspects, source, reservoir, traps. Prospect identification, reservoir seal, source rock presence, timing and trap of hydrocarbon migration, how cooked it is, if are we getting an oil from it, are we getting gas from the particular basin, and then sedimentary geology, new data for exploration, drilling a discovery well, a field development. These are the role of geologists which they do before exploiting a particular field. This is somehow a geologist. I mean, you can see what even sketches. This is a donkey kind of drill which pulls out all the oil and oil. Something. These are on the right sketches made up of logs. This is a oil mill, and they are studying everything. This is the role of a geologist in exploration and production. And oil and gas, from all at the end of this lecture, I can call it as a black gold. And I think you wouldn't have any problem to call it as a black gold. Producing, powering our economy, human lives, everything. Moving on to the next. So these two images, they are like a century of exploration. 1907, Sanga, this is an oil well. They have encountered a huge oil reserve, and this oil is present in a really tremendous amount of pressure. So when you prick it, you will eventually make a fountain come out of it. So the fountain is coming out, and on the right, you can see we have reached into the seas. We are now navigating the seas. We are riding the waves, and getting the oil out from the seas. You can see how unhappy the sea is. This is North Sea UK 2007 picture. 1907, where we were in exploration and exploitation, and 2007, where do we stand? So this is the growth which these two pictures show us. Moving on to the next, this is for you guys. I mean, geologists, what does geology actually do? At the end of the day, they just solve puzzles. Everything is present beneath the earth. What we do, we just solve puzzles. This is for you to solve out. I won't tell about it. I'll just show you what has happened. This is position 1. What have we seen? 2 different types of footprints, here and here. Move on to the next. What happened? All these footprints, they're together now. Okay, position 3. What has happened? Has the bigger one eaten the smaller one? Or the bigger one was the mother of the smaller one and now it has carried its back? It's for you to decide. Thanks.